There's a moment when you look up at the night sky and feel something stir inside you, a longing that has no name, a pull toward lights that will never touch your skin. Alpha Centauri glimmers there, 4 light years away, close enough to see, too far to ever reach. What if I told you that the distance between us and that star is not just space, but a mirror reflecting every limit we've ever faced? What if the real journey to the stars isn't measured in speed, but in the courage to accept what the universe is trying to teach us? Before we drift into the impossible, let me ask you something that might change how you see everything tonight. If you could send your consciousness to another star, leaving your body behind, would you go? Would you abandon everyone you love, every memory tied to Earth, just to see what's waiting in the light of an alien sun? Keep that question close as we travel together through the dark. One more thing before we begin. Imagine you're the last human alive, and you have enough power to send one final message to Alpha Centauri, knowing it will take 4 years to arrive and no one may ever answer. What would you say to the silence? Hold that thought. We're going to need it. Like and subscribe before the stars shift. It keeps this journey alive through the void. Tonight we follow light across distances that break the soul. Let's begin. Just beyond our ability to touch lies a system of 3 suns locked in an eternal dance. Alpha Centauri, A burns yellow and bright, almost a twin to our own star. Its companion, Alpha Centauri B, glows softer and more orange, circling in an orbit that takes 80 years to complete. And far out in the cold dark, so distant it seems almost forgotten, Proxima Centauri flickers like a dying ember, the nearest star to Earth yet invisible to the naked eye. Together they move through space in a choreography billions of years old, bound by gravity's invisible thread. When you glimpse Alpha Centauri on a clear night in the southern hemisphere, you're seeing something that looks deceptively simple, a single point of golden light. But in truth, you're witnessing 3 separate worlds of fire, each one a furnace of fusion, each one utterly unreachable by anything we've ever built. The light that touches your eyes tonight left those suns 4 years ago, before this moment existed, before your last birthday, before countless decisions that shaped who you are now. Every photon is a messenger from the past, arriving silently to tell you a story about distance and time. 4 light years. Just 4. The number sounds almost friendly, manageable even. After all, light crosses that distance in only 4 years, a blink on cosmic scales. But the universe hides cruelty behind simplicity. 4 light years is a chasm so immense that every spacecraft we've ever launched collapses under its weight. Voyager One, traveling faster than any human-made object in history, would need over 75,000 years to reach Alpha Centauri. 75 millennia, longer than modern humans have walked upright. If we launched it today, it would arrive in a future where our languages had evolved into something unrecognizable, where our cities had turned to dust, where our species itself might have become something else entirely. The people who sent it would be legends so ancient they'd be indistinguishable from myth. And yet that distance calls to us with a voice we cannot ignore. Scientists have detected a planet there, Proxima b, orbiting in the habitable zone of the smallest sun. It might have water. It might have air. A world so close, we can already measure the faint dimming of starlight as it passes in front of its sun. But between our world and that one lies an ocean of darkness so vast that even hope travels slowly through it. This is the strange contradiction at the heart of interstellar travel. Alpha Centauri feels near enough to touch, yet impossibly far to reach. We can calculate its distance with precision, photograph its light, chart its movements across our sky. But those calculations only deepen the ache. When we understand exactly how far 4 light years truly is, we begin to grasp the terrible mathematics of forever. Perhaps that is the truest measure of cosmic distance. Not how far something is, but how long its voice takes to reach us, and how many generations will die before we could ever answer back. Light moves at 300,000 kilometers per second, fast enough to circle Earth 7 times in a single heartbeat. At that velocity, light itself becomes almost miraculous, a cosmic speed limit written into the fabric of reality. It races through the vacuum carrying information, energy, and the story of everything it touches. Photons born in the hearts of stars stream outward in all directions, some finding eyes after journeys that span millennia. Every sunrise, every reflection on water, every glimmer in the night sky is testimony to this ancient traveler. Yet for all its speed, light reveals the cruelest truth about the universe. That vastness exceeds even the swiftest messenger. That the cosmos is built on a scale that makes velocity itself seem slow. When we say the speed of light, we often imagine it as limitless, as though it were a key that could unlock everything. But nature draws a hard boundary there, absolute and unforgiving. No ship, no signal, no dream can outrun it. Einstein showed us why. As an object accelerates, it gains mass. The faster it moves, the heavier it becomes. Push toward light speed and mass approaches infinity. The energy required to make that final leap becomes infinite as well. It's not just difficult, it's impossible by definition. The universe doesn't merely discourage faster-than-light travel. It forbids it with mathematical certainty. So light is not just fast, it is sacred. It defines what is possible and what will remain forever out of reach. Astronomers call it C, a single letter that governs all of relativity, all of space-time, all of motion itself. Even time bows before it. At light speed, clocks stop ticking. Lengths contract. The universe becomes something strange and fluid, a place we can describe with equations but never truly inhabit. Every observation we make of the cosmos is really a glimpse backward through time. The sun you see in the morning sky is already 8 minutes old. The nearest galaxy sends us light that began its journey 2.5 million years ago, when early humans were just learning to create fire. Even your reflection in a mirror is delayed by the tiniest fraction of a second, the time it takes light to travel the width of your face and return. This is the paradox. Light moves faster than anything in existence, yet it always arrives late. When we look at Alpha Centauri, we see it not as it is, but as it was 4 years ago, frozen in time, preserved in the motion of photons that have already moved on. To reach another star would mean chasing ghosts, pursuing messengers that left long before we began following. In a universe governed by the speed of light, catching your own reflection becomes as impossible as reversing entropy. Light is both our window and our wall, the fastest path through the cosmos, and the barrier that keeps us confined within our small corner of it. If we launched Voyager One directly toward Alpha Centauri, it would take more than 75,000 years to arrive. By the time it reached those distant suns, every civilization we know would have risen and fallen. Voyager One is humanity's farthest castaway, launched in 1977 on a mission to explore the outer planets. It succeeded beyond all expectations, sending back the first close images of Jupiter and Saturn, revealing moons and rings that rewrote our understanding of the solar system. Then it continued outward, past Uranus, past Neptune, past the edge of the solar wind itself. Today it drifts in the interstellar dark, 24 billion kilometers from home, still sending faint signals that take over 22 hours to reach Earth. Yet even now, after nearly half a century of travel, it has crossed less than 1% of the distance to the nearest star. The spacecraft carries a golden record, a message to anyone who might find it. Sounds of Earth, greetings in 55 languages, music from Bach to blues, the laughter of children, the crash of ocean waves. Etched onto its surface is a map showing our location among nearby pulsars, a cosmic address written for beings we will never meet. If Voyager continues on its current trajectory, undisturbed and untouched, it will reach the vicinity of another star in 40,000 years. By then, Earth's continents will have shifted. Mountain ranges will have risen and worn away. The languages recorded on that disk will be as ancient and incomprehensible as the earliest human cave paintings are to us now. The civilizations that built Voyager will exist only as archaeological mysteries, if they exist at all. 75,000 years is a span of time that barely fits inside human imagination. When Voyager launched, our fastest spacecraft could reach the Moon in 3 days, Mars in months. But the leap from planetary to interstellar distance is not linear. It's exponential. The same engines that carried us to the outer planets become almost meaningless across the gulf between stars. Chemical propulsion, the technology that powered every space mission in history, burns bright but inefficient. Rockets work by expelling mass in one direction to create thrust in another. The faster you want to go, the more fuel you need. But fuel has mass, and more mass requires more fuel to lift it, creating a vicious cycle that quickly spirals into impossibility. To accelerate even a small spacecraft to 1% of light speed using chemical fuel would require more propellant than exists in the observable universe. The rocket equation is merciless in its honesty. For interstellar missions, chemical propulsion isn't just inadequate. It's absurd. Even our most powerful rockets, burning liquid hydrogen and oxygen, can achieve velocities of only about 17 kilometers per second. To reach Alpha Centauri in a human lifetime would require speeds of tens of thousands of kilometers per second. The gap between what we can do and what we need is so vast it might as well be infinite. And yet those rockets represent something profound. Every launch is an act of defiance against gravity, against inertia, against the tyranny of staying still. The sight of a rocket ascending through clouds, trailing fire and sound, is more than engineering. It's a declaration that we were never meant to remain bound to one world. Chemical propulsion carried us to the Moon, sent probes to every planet, and flung Voyager into the interstellar night. It's the technology that taught us how to leave home. But it's also the anchor that keeps us from going farther. The same fire that lifted us skyward now binds us to the solar system, unable to burn long enough or hot enough to cross the distance to another star. Escaping Earth's gravity is difficult. Escaping the sun's gravity requires unimaginable energy, and most spacecraft never truly leave its embrace. We think of space as freedom, a place beyond the pull of any world. But even in the silence between planets, we remain tethered. The sun holds every object in the solar system within its gravitational grip, an invisible hand that extends billions of kilometers in every direction. To leave that dominion entirely, to step beyond the frontier where the sun's influence fades, to nothing, demands energy on a scale we've barely begun to imagine. Every spacecraft begins its journey in layers of escape. First, it must break free from Earth, clawing upward against a planet that pulls with relentless force. That alone consumes the majority of a rocket's fuel, just to reach orbit a few hundred kilometers above the surface. But escaping Earth is only the beginning. Our planet itself is falling endlessly around the sun at 30 kilometers per second. To truly leave the solar system, a spacecraft must counter that momentum and climb out of the sun's gravitational well. The math is brutal. A rocket needs about 11 kilometers per second to escape Earth. To escape the sun's gravity entirely from Earth's orbit requires at least 42 kilometers per second, nearly 4 times faster. Voyager achieved this by slingshotting around the giant planets, borrowing momentum from their orbits like a stone skipping across water. Even then, it moves slowly by interstellar standards. The sun's gravity diminishes with distance, but never truly vanishes. Even at the edge of the heliosphere, where the solar wind gives way to the interstellar medium, the sun's mass still exerts a pull. Voyager is free in the sense that it will never return, but it remains bound to the sun's orbit around the galactic center. For billions of years, it will circle the Milky Way alongside us, a permanent citizen of our stellar neighborhood. Imagine the sun's gravity as a deep well, invisible but ever-present. Earth sits near the bottom, held in place by the star's immense mass. The farther out you climb, the weaker the pull becomes. But escape is never complete. Every kilometer away from the sun is a step uphill against this tide. For humanity, this creates a paradox. The energy required to reach another star must first be spent just leaving our own. The sun, the source of all our warmth and life, is also the gatekeeper of our cosmic prison. Even the most powerful engines we can imagine, fusion drives or antimatter, reactors, must first pay this toll before they can accelerate freely toward the stars. At near light speeds, time itself becomes relative. For travelers aboard a ship moving at 99% of light speed, only years might pass. But on Earth, centuries would slip by. This is not theory. It's one of the most tested and verified predictions of Einstein's relativity. Time dilation is real, measurable, and absolute. Astronauts aboard the International Space Station age slightly slower than people on the ground. GPS satellites must account for relativistic effects, or their timing would drift, rendering them useless within hours. These differences are tiny, fractions of a second, but they prove the principle. At velocities approaching light speed, time itself warps. Imagine a crew departing Earth on a journey to Alpha Centauri at 99.9% of light speed. From their perspective, the voyage might take only a few years. They would age normally, eat meals, sleep, and watch the stars slowly shift position outside their windows. But back on Earth, decades would pass. By the time they sent a message home, the people who launched them might be dead. When they returned, if they ever did, centuries would have elapsed. Their families would be dust, their languages unrecognizable. The world they left would exist only in history. This is the deepest cost of relativistic travel. You can reach the stars within a lifetime, but you can never go home. To outrun time is to lose the context of your own existence, to become a ghost unmoored from history. Every choice to travel faster is also a choice to leave behind everything you've ever known. The universe allows motion, but it demands exile in return. Perhaps this is why the stars feel so lonely. Not because they're far, but because reaching them means stepping outside of time itself, becoming a wanderer in a future you can never be part of. To accelerate a single ton to half the speed of light requires more energy than all of humanity produces in a year. Think about that. Every power plant, every generator, every battery, every drop of fuel burned across the entire planet for 12 months, just to move 1 ton halfway to light speed. And that's only acceleration. To stop at the destination would cost the same again. The energy wall is not a metaphor. It's a physical barrier as real as any mountain, and it rises exponentially with every increase in velocity. Double your speed and you need 4 times the energy. Go 10 times faster, and you need 100 times more. The universe charges compound interest on haste, and the debt becomes unpayable long before you reach relativistic speeds. This is why antimatter, despite its theoretical perfection, remains a fantasy. When matter meets antimatter, they annihilate completely, converting mass directly into energy according to Einstein's equation. The efficiency is unmatched. A single gram of antimatter reacting with a gram of matter releases as much energy as a small nuclear bomb. In theory, a spacecraft powered by antimatter could reach significant fractions of light speed. In practice, creating antimatter consumes far more energy than the annihilation releases. Producing a single gram would require the total energy output of the United States for an entire year, and we'd need to produce it continuously, store it without loss, and somehow convince it not to annihilate with the walls of its container. Every solution spawns 10 new problems. Storage alone is a nightmare. Antimatter cannot touch ordinary matter without vaporizing both in a flash of gamma rays. It must float in magnetic traps, cooled to near absolute zero, suspended in perfect vacuum. A power failure, a cosmic ray strike, even a slight vibration could trigger catastrophe. The ship wouldn't fail. It would detonate. Fusion offers a gentler dream. In the core of every star, hydrogen nuclei collide and merge, releasing energy that lights the cosmos. If we could recreate that process in a controlled way, sustaining it long enough to produce thrust, we could build engines far more efficient than anything chemical. Fusion-powered spacecraft could theoretically reach 10% of light speed, cutting the journey to Alpha Centauri from millennia to mere decades. But despite billions of dollars and decades of research, we still can't make fusion last longer than seconds. The plasma is too hot, too unstable, too unwilling to be tamed. Every experiment inches closer to break even, the point where output equals input, but practical fusion propulsion remains perpetually 20 years away. So we return to patience. Light sails offer an elegant alternative: propulsion without fuel, motion without combustion. A vast reflective sheet catches photons from the sun or from powerful Earth-based lasers, and those tiny impacts accumulate into thrust. It's almost poetic. Motion powered by light itself. The Breakthrough Starshot Initiative proposes sending swarms of tiny spacecraft, each weighing only grams, to Alpha Centauri. Lasers on Earth would push them to 20% of light speed in minutes. They could arrive in just over 20 years, fast enough that the people who launched them might still be alive to receive the data. But the challenges are immense. The sails must be kilometers wide, yet weigh almost nothing. They must survive decades of bombardment by interstellar dust, any grain of which could tear through the delicate material like a bullet. There's no way to slow down. These probes would flash through the Alpha Centauri system in hours, capturing what data they can before vanishing forever into the dark. They are messengers designed for a single glimpse, explorers who will never return. And what of the human cost? Our bodies evolved for Earth, one atmosphere of pressure, a steady pull of gravity, the protection of a magnetic field that shields us from the worst of cosmic radiation. Step beyond that invisible boundary and we begin to unravel. In microgravity, muscles atrophy and bones dissolve. Calcium leaches from the skeleton at a rate of 1% per month. The heart weakens. Fluid shifts upward, swelling faces and blurring vision. The immune system falters. Wounds heal slowly. Every moment in weightlessness is a slow negotiation with decay. But physical degradation is only the beginning. Outside Earth's magnetosphere, cosmic rays tear through DNA like invisible knives. Radiation from solar flares and distant supernovae bombards everything with high-energy particles. On a journey to Alpha Centauri, astronauts would absorb doses far beyond anything survivable. Even with shielding meters thick, the cumulative exposure would be lethal. And then there's the psychology. Months of isolation can fracture minds. Years would erode them. Imagine spending decades in a metal tube, surrounded by the same faces, the same walls, the same recycled air. No sunlight. No seasons. No horizon. Time would lose meaning. Sleep would fragment. Madness would creep in like a slow tide. To survive such a journey, humans would need to become something different. Genetic modifications to resist radiation. Neural implants to stabilize mood. Cryogenic sleep to skip the waiting. Each solution pushes us further from what we are. The paradox is inescapable. To reach the stars, we may have to surrender our humanity. And if we do, what arrives at Alpha Centauri won't be us anymore. It will be something we created, something that remembers Earth but can no longer call it home. Perhaps that's acceptable. Perhaps transformation is the price of transcendence. Or perhaps the real journey is not outward but inward, learning to expand consciousness rather than distance. When we look at Alpha Centauri through telescopes, measuring its spectrum and mapping its planets, we are already touching it in the only way that truly matters. Light from those suns crosses the void and enters our instruments, carrying information across 4 years of darkness. In decoding that light, we hold a piece of those distant worlds within our minds. Maybe this is how humanity conquers space, not through ships or engines, but through understanding. Every photon that reaches us is a messenger. Every equation we solve brings the stars a little closer. The boundaries we face are not walls but invitations, challenges whispered by the universe itself. It asks not whether we can overcome them, but whether we're willing to try. Because the act of striving, the refusal to accept that distance means never, is what defines us. We are the species that looks up. In all the vastness of the cosmos, in all the cold silence between galaxies, we are the ones who wonder. Somewhere in the universe, consciousness emerged from matter and began asking questions. That alone is miraculous. That we exist at all, that we can comprehend light years and relativity and the curvature of space-time, is more extraordinary than any voyage we might undertake. So Alpha Centauri remains 4 light years away, both near and infinitely distant. A reminder that some barriers exist not to imprison but to inspire. The stars may be unreachable, but the longing for them shapes everything we do. Every discovery, every innovation, every dream we pass to the next generation extends the reach of awareness a little farther. One day, perhaps millennia from now, our descendants might stand beneath an alien sun and remember the people who first looked up and dared to imagine this moment. They will carry our curiosity forward, transformed but unbroken, proof that even the longest journeys begin with a single impossible dream. Until then, we remain here, staring across the abyss, sending light into the darkness and waiting for it to return. Good night.